Picture this for a second. You're holding your phone and you tap pay on your mobile banking app. In literally a fraction of a second, an API call is fired off. It navigates a highly secure authentication layer. Database transactions are rigorously verified. Error handling protocols stand by just in case. And boom, a confirmation pops up on your screen. That invisible, highly coordinated ballet, that isn't just programming. That is the rigorous discipline of software engineering. Welcome to this explainer. Today we're going to explore exactly what happens behind the scenes when we build these massive, complex platforms. And we'll move systematically through those layers of authentication, databases, and APIs. Now, you might be thinking, isn't this really just writing code, sitting in a dark room, typing out scripts? But when you consider a highly complex computerized financial system, or say an aviation control matrix with unbounded state spaces and absolute zero tolerance for failure, is it really that simple? Well, the answer is a hard no. Writing a few lines of code to solve a math problem in a controlled environment is fundamentally different from engineering a system that has to be highly reliable, economically viable, and maintainable by hundreds of different developers over decades.
Actually, there's a fantastic historical observation that perfectly illustrates why this discipline even had to be invented. It comes from the 1968 NATO conference, which is where practitioners first articulated what they famously called the software crisis. They realized that building software the way early inventors built airplanes, just pushing it off a cliff to see if it flies, was leading to absolute massive project failures. Take the infamous Mariner 1 spacecraft crash, for example. That multi-million-dollar probe was destroyed shortly after launch, all because of a single missing hyphen in the code. Seriously, one hyphen. This crisis absolutely forced the industry to shift away from a localized individual craft into a disciplined, highly structured engineering science. So here is our roadmap for today. We're going to move from the macro theory of engineering, dive deep into core design principles and the software development lifecycle, compare agile methodologies, and then zoom back out to look at long-term software evolution and maintenance.
All right, let's kick things off with Section 1, Beyond Just Coding. The crucial point we need to establish right away is the definitional contrast here. Computer science, that provides the foundational theory. It gives us the mathematical models, the complex algorithms, and defines the literal limitations of computing. But software engineering, especially as defined by the IEEE, is the systematic, disciplined, and quantifiable approach to the development, operation, and maintenance of software. It is strictly concerned with the gritty practicalities. How do you develop software in massive teams, satisfy very precise customer requirements, and actually deliver a product within budget and on a strict schedule? And honestly, engineering is this massive umbrella. Think about how distinct disciplines all connect. Whether you are dealing with front-end user interfaces, back-end databases, full-stack integration, deeply embedded systems, or massive cloud architectures, they are not isolated islands. Every single one of them relies on the exact same fundamental framework of planning, design, testing, and implementation to function cohesively. Which brings us right to Section 2, Core Principles of Design. Because before a single line of code is ever written, these systems must be carefully architected. First up, we have modularity. This is absolutely essential. Breaking a massive system down into smaller, self-contained pieces is literally the only way to make a large program intellectually manageable. Modularity enforces what we call the separation of concerns, which basically allows a massive engineering department to divide and conquer. It enables parallel development. That means different teams can build completely different components at the exact same time without constantly stepping on each other's toes. Next is coupling, which measures exactly how much one part of the software depends on another. As engineers, our absolute holy grail is loose coupling. By keeping these strict dependencies between these modules to an absolute minimum, we prevent what are known as cascading system failures. Basically, it means the back-end database team can push an update to their module without accidentally completely breaking the front-end user interface. And this builds directly into another core concept, abstraction. Abstraction is a cornerstone of computer engineering. It's all about hiding those incredibly complex, under-the-hood implementation details behind very simple, well-defined interfaces. Think about it. This is exactly how RESTful APIs function. They separate what a component does from exactly how it does it, which makes the entire software architecture infinitely easier to understand, to test, and to integrate. Moving a bit deeper, we universally apply the DRY principle. Don't repeat yourself. This ensures that every single piece of knowledge or data has one single unambiguous representation in the system. And let me tell you, that massively reduces bugs when things need to be updated. We also rely heavily on the broader solid principles. For instance, the dependency inversion principle.
This ensures that we purposefully decouple our high-level logic modules from our low-level technical details, which further insulates the whole architecture against disruptive, unexpected changes. Okay, moving right along to Section 3, the Software Development Lifecycle. It all starts right here with requirements engineering. Listen, skipping this step is the single fastest way to build the absolute wrong product. We must rigorously elicit, analyze, and validate what the stakeholders actually need. This phase produces the strict specifications that guide the entire rest of the project, and it ultimately prevents incredibly expensive redesigns later on. Seriously, a bug found way out in production can cost up to 100 times more to fix than a conceptual flaw caught right here in the design phase. Once those requirements are totally locked in and the coding finally begins, that code does not just go straight to the end user. Not a chance. It moves through very distinct, isolated environments. It starts on a developer's local machine IDE, then it moves to an integration server via automated CI/CD pipelines, then over to testing and QA for rigorous unit and end-to-end checks. From there, it goes on to a staging replica, often containerized with tools like Docker, and only after surviving all of that is it finally pushed to the live production environment. And throughout this entire pipeline, having robust version control using Git, strict branching strategies, and a hardcore culture of peer-reviewed code, usually via pull requests on GitHub or merge requests on GitLab, these are absolute necessities. You have to systematically track every single change. Because if a catastrophic bug somehow makes it all the way to production, version management is your ultimate undo button. It allows engineers to instantly roll back the system to a previous safe state, protecting the integrity of the whole platform. So, how do teams actually organize all this work? Let's get into Section 4, methodologies, basically looking at Waterfall versus Agile. So here we can directly compare the historical heavyweights of the industry. On one hand, we have the predictable, rigid, and sequential phases of Waterfall. It is fantastic for predictability, but man, is it highly inflexible. Contrast that directly against the highly adaptive, iterative nature of Agile. Born directly from the famous Agile Manifesto, this approach strictly prioritizes working software and direct customer collaboration, which lets teams handle rapidly changing business requirements so much more effectively. And under that broader Agile umbrella, we find very specific frameworks like Scrum. Scrum relies on what's called empirical process control. It organizes self-managing, totally cross-functional teams to build, test, and integrate features within strict time-boxed iterations that we call sprints. It's highly dynamic. It allows huge projects to constantly adjust their course based on the actual completed work, rather than just guessing up front and hoping for the best. Finally, let's zoom back out for Section 5, software evolution and maintenance. Remember this if you remember nothing else. Software is not manufactured on an assembly line. It is engineered. And because of that, it has to continuously evolve in a spiral process. Once version 1 is out the door, it immediately enters an evolution phase to meet constantly shifting business needs before eventually transitioning into a long servicing phase and ultimately a phase out when it is finally replaced. In fact, for large custom enterprise systems, the long-term cost of maintenance almost always far exceeds the initial development costs. Whether a team is fixing late-stage bugs, adapting the whole system to run on new cloud computing architectures, or refactoring legacy code, which, by the way, as Martin Fowler describes, is the act of improving internal structure without altering external behavior, maintenance is truly where the bulk of software engineering actually happens day in and day out. So, to bring this all together, what are the 3 major takeaways you should leave with today? Number 1, software engineering is a systematic, highly quantifiable discipline. It is definitively not just writing code. Number 2, core principles like modularity and abstraction are literally the only things preventing large-scale system chaos. And number 3, software is never truly finished. It requires continuous, active evolution and maintenance. As we look toward the future, especially with the rapid rise of AI-assisted development paradigms, low-code tools, and immensely complex, globally distributed systems, these foundational engineering principles are only going to become more critical to master. Because with software systems increasingly unbounded by physical limits, we have to ask ourselves, how will we engineer the unmanageable, distributed platforms of tomorrow? If you want to dive deeper into system architectures or agile workflows, make sure to check out the resources linked below. Subscribe, visit course, download resource. Thanks so much for learning with me today.